In this lecture, we'll introduce the concept of resistance, which is useful to describe the behavior of some elements that commonly show up in electrical circuits. First, however, we're going to discuss a simplified way to represent a circuit. In an earlier lecture, we represented a simple single-loop circuit with an energy source, represented here as a battery, and colored figures to represent other elements, all connected together to provide a complete round-trip path for the conventional current I to flow. You'll also recall that we introduced the loop rule, which describes energy conservation in the circuit. Now, it's commonly the case that some elements in the circuit are performing some function, and other elements are there simply to complete the path that enables the current to flow. For example, imagine that the orange element represents an incandescent light bulb that lights up when the current flows, while the cyan and red elements here represent wires that connect the light bulb to the battery. Here's a somewhat more realistic picture of this. Now, the role of the wires is simply to complete the circuit. In any good design, we'd want very little of the energy from the battery to end up in the wires. That means we'd like the potential differences across the wires, delta V1 and delta V3 in this example, to be quite small. That would then mean the potential difference delta V2 would be the only significant potential difference other than the potential difference across the battery. And therefore, to a good approximation, our loop rule would look like this. So in order to pay attention to only those elements in a circuit that matter from an energy perspective, we will represent circuits like this in what is known as a lumped element circuit model. So the orange element on the right, which plays a significant role in the circuit, like the light bulb in our light bulb circuit, has some potential difference, delta VE, that we need to pay attention to, along with the potential difference across the energy source, delta V battery here. The important elements are represented by discrete pieces, or lumps, if you will. Other elements that are necessary but simply serve as connections to complete the circuit will represent by thin lines shown in black here. And we'll assume the potential differences across these lines are all zero. So the loop rule will only contain those potential differences of significant elements, just as we show here. We can treat a large class of circuit elements, say like the filament in an incandescent light bulb, in the following manner. Imagine we have a steady state conventional current, capital I, flowing through the element, as we show here, and we measure a potential difference, delta V, across the element. We can define a quantity called the resistance of the element as the ratio of the magnitude of the potential difference divided by the current. In the SI system, the unit of resistance is volt per ampere, which is more commonly called an ohm, and is often symbolized with the Greek letter capital omega. The concept of resistance is most useful when the elements are made of materials where the ratio, capital R, is constant. In that case, this relationship is called Ohm's law. For cases like light bulb filaments, Ohm's law is approximate. However, Ohm's law is a very good description for very common circuit elements called resistors. There's a microscopic way to look at resistance. In an earlier lecture, we discussed how the conventional current I could be related to the charges that flow with an average drift velocity, vector v sub d here, across the cross-section of an element of area capital A. The expression for capital I also depended on n, the density of mobile charges, as well as the magnitude of each charge in the current. We now know the reason charges keep flowing is that there is a non-zero electric field inside the element. The drift speed, the magnitude of the drift velocity, is proportional to the magnitude of the electric field, where the constant of proportionality, U, is called the mobility and is a material property of the stuff from which the element is made. Now, if we substitute this relation into our expression for capital I and use the fact that the magnitude of the electric field can be expressed in terms of the potential difference, delta capital V divided by delta L, the length of our element, Then, with some rearrangement, we end up with this expression, which is, in fact, Ohm's law, where the quantities in the parentheses are altogether just the inverse of the resistance of the element. Here we write out the expression for the resistance explicitly, which contains the geometry of the element, length delta L and cross-sectional area capital A, and material properties of the element, which altogether are commonly given the Greek symbol sigma and are called the conductivity of the material from which the element is made. Let's now return to our simple circuit where we represent the resistive element with the short zigzag line in this lumped circuit element representation of a single loop circuit with an energy source and a single resistor. Note that in a circuit analysis involving a resistor, the potential difference delta VR is negative when we move across the resistor in the direction of the conventional current I. Here is the loop rule, where we can use Ohm's law to relate the magnitude of delta VR to I in the resistance R. We will use these ideas to discuss some ways to handle circuits with multiple resistors in special combinations in our next lecture.